Hello and welcome to Dark Matter and Dark Energy, the most mysterious stuff in the universe. The last lecture in my 6-part lecture series, Cosmology, the Study of the Universe. My name is Fulvia Fiorani. Everything that we have talked about up to now, all of the hundreds of billions of galaxies, each containing hundreds of billions of stars, in other words, all of the ordinary matter in the universe, makes up only 5% of our universe. The remaining 95% is made up of dark matter and dark energy, and yet we know so little about it. In this lecture, we will attempt to answer questions such as, what is this stuff? If we can't see it, how do we know it's out there? How does it affect the evolution of our universe? And how will it affect its future? The most exciting answer to these questions is, we simply don't know. This field raises many more questions than it provides answers, and that's what makes it so exciting. What I will attempt to do today is to give you a general idea of what we know so far. The study of dark matter and dark energy attempts to answer one of the oldest human questions: what is the universe made of? What we call ordinary matter is about 5% of the universe. Ordinary matter includes all the stars. There are over 100 billion galaxies, each containing hundreds of billions of stars. All the interstellar gas and dust, mostly made of primordial hydrogen and helium, all the neutrinos, and all the heavy elements. Basically, everything we can see only makes up 5% of the universe. Dark matter makes up about 27%, while dark energy makes up about 68%. Now, we have a pretty good grasp on the 5% of ordinary matter, but what we know very little about is the remaining 95%. And it is, of course, this 95% that we will focus on today. Now, you might ask, how do we know that everything we see out there makes up only 5% of the universe? And if we can't see the remaining 95%, how do we know that it's out there? Well, my hope is that by the end of this lecture, this pie chart will make a little more sense. So how will we get to that understanding? Well, before tackling the great unknown, we start with some preliminary concepts of space, time, and gravity, and I promise only 4 equations. Then we go to dark matter. We will see what evidence we have for its existence, and then describe the best candidate for a dark matter particle. And we will end the dark matter portion with a quick look at some of the ongoing research projects. Our next topic will be dark energy. We will see how the story of dark energy starts with the discovery that the expansion of the universe is accelerating. Dark energy is what drives this acceleration, but we don't really know what it is. So we'll talk about some of the current possibilities. We start our look at space, time, and gravity with classical mechanics of Isaac Newton. For Newton, space and time are separate entities. Space and time exist independently from each other. Space and time are absolute, or they are the same for everyone. The rate at which time flows, or the distance between 2 objects, does not depend on who you are or how you're moving through space. And space and time are fixed. They do not change into something else. Space and time are always the same throughout the universe. Now, these are very intuitive ideas. Newton was the first to describe and formulate a law of gravity. For Newton, gravity is an attractive force between bodies or between masses. This is his law of universal gravitation. It quantifies and describes the force of gravity between 2 bodies as being proportional to the product of their masses, so the larger the masses, the stronger the force, and inversely proportional to the square of their distance. So if you double the distance, the force goes down by a factor of 4, and if you triple the distance, the force goes down by a factor of 9. Now, for this lecture, we will only use this as it relates to orbital motion. An example is our solar system. Because the force of gravity decreases with distance, the outer planets will feel a smaller force. Therefore, their orbital speed must be slower than the inner planets, otherwise they would simply not be able to stay in orbit. For example, the orbital speed of Mercury, the closest planet to the Sun, is approximately 100,000 miles per hour, while Neptune's, the farthest planet, is approximately 12,000 miles per hour. We will see that this is a very important concept in establishing the existence of dark matter. So remember, the orbital speed decreases as we move farther away from the central mass. About 200 years after Newton, Einstein published his famous theory of special relativity. Now, this is not as intuitive as Newton's ideas. Whereas for Newton, space and time are two separate entities, for Einstein, space and time are simply two different aspects of the one four-dimensional space-time. So we still have a fixed structure, but now it's only one instead of two separate entities. Now, although space and time are still fixed in special relativity, they are no longer absolute. The measurement of space and time actually depends on who is making the measurement and how fast they are moving. We say that space and time are relative to the observer. Another great outcome of special relativity is the equivalence of mass and energy, better known in its equation format, E equals mc squared, which states that energy is equal to mass times the speed of light squared. Now, we have already seen and talked about this equation a few times during this series. And this equation lies at the core of modern physics. And this concept is very important. It tells us that mass and energy are interchangeable. In essence, they are the same thing. Now, after the success of special relativity, Einstein tried to incorporate gravity into special relativity. And it took him 10 years, and in the end he realized they were incompatible. So he had to throw out Newton's extremely successful theory of gravity and replace it with general relativity. Perhaps Einstein's greatest insight was that the very structure of space and time is dynamical. In other words, space itself can actually change. It is no longer fixed. So space-time has a geometry and a curvature, and it is that curvature that we interpret as gravity. Here we see a diagram that represents the warping or the curvature of space by a mass. The typical example is a rubber sheet with a bowling ball in the center. The sheet will curve depending on the mass of the bowling ball. If you then place a marble near the bowling ball, it will move according to the curvature of the rubber sheet. So gravity is simply a manifestation of the curvature of space. Now, there is a universal coupling between the curvature of space-time and everything in the universe. If something exists in any physical form, whether it be mass or energy, it will give rise to a gravitational field. Now, what is important for this lecture is that it can go the other way as well. If we detect a gravitational field, there must be mass and/or energy present. This is one of the ways that we will infer the existence of dark matter. Now, even light will bend according to the curvature of space. This was, in fact, the first observational proof of general relativity. So here we see that light from a star in position A will follow the curvature of space caused by the sun, and will appear to be coming from position B. This was successfully proven during a solar eclipse in 1919. This phenomenon is called gravitational lensing, and we will use it to convince ourselves of the presence of dark matter. Now, I cannot overstate the importance of general relativity. It is the best description of the basic properties of space and time, the best description of how gravity works, and the best description of how the universe works as a whole. Now, these are the last two equations that we will see. The only reason I mention these is because we will occasionally refer to them as the equations that cosmologists use to study the universe. It is not important to understand the math, just a general idea of their meaning. The first one is Einstein's equation. The left side of the equation tells us the curvature of space, while the right side tells us the energy and mass content of the universe. So essentially, this equation tells us how much space is curved and that everything, mass and energy, contributes to the curvature of space. The next one is the Friedmann equation. It is derived from Einstein's equation and describes the expansion of the universe. Therefore, it is the most important equation in cosmology. Rho is the energy density of everything in the universe. H is the expansion rate of the universe, represented by the Hubble constant. And K is the curvature of space, and it incorporates Einstein's equation. So this equation tells us how the expansion of the universe responds to the stuff that is in the universe. Okay, now that we are armed with all of this physics, let's get to dark matter. We don't actually know what dark matter is, but we do know that it's out there. So how do we know? Well, we infer its existence through its gravitational effect. So how will we convince ourselves of that? Well, the first way is through the study of motions of galaxies. We will look at motions within individual galaxies and the motion of galaxies within clusters. The second method is through gravitational lensing. And the last method is through analysis of the cosmic microwave background. We start with getting a general idea of what we mean by a galaxy and clusters of galaxies. So a galaxy is a collection of gravitationally bound stars. On average, there are about 100 billion stars in a typical spiral galaxy. All the stars orbit the center of the galaxy. For example, it takes our sun about 250 million years to complete one orbit. And amazingly, we can use good old Newtonian mechanics to study the motion of stars and gas within a galaxy. A cluster of galaxies is a system of gravitationally bound galaxies. They are the largest gravitationally bound systems in the universe. Every point of light we see here, with the exception of a few foreground stars, is a galaxy. Galaxies within a cluster orbit the center of the cluster. The first observational evidence of the effect of dark matter was put forth by the Swiss astronomer Fritz Zwicky in 1933. Although he was Swiss, he worked most of his life at the California Institute of Technology. Now, his goal was to weigh the largest astronomical object he could find, in this case, the Coma cluster. Now, to weigh a galaxy or a cluster of galaxies means to try to determine the mass content. One way is to simply look and count. The average galaxy has about 100 billion stars, and the average star is like our sun, so on average, galaxies weigh approximately 100 billion solar masses. But Zwicky wanted a better way, so he used gravity. He reasoned that since everything contributes to a gravitational field, if we can measure the gravitational field of a cluster, we can then determine how much stuff is in the cluster to produce the observed gravitational field. So to determine the gravitational field of the cluster, Zwicky measured the velocity of galaxies as they moved around the cluster. From those velocities, he was able to calculate what the mass of the cluster should be to support those velocities, much like the way we calculate the mass of the sun by the velocities and distances of the orbiting planets. Once he calculated what the mass should be, he compared it to the visible mass within the cluster. What he found was that the galaxies were moving too fast. His calculations implied that the cluster contained 50 times more mass to support their velocities than could be visibly accounted for. His conclusion was that there must be matter out there that we don't see. In his paper, he called this unseen matter dark matter. Despite its catchy name, Zwicky's results were regarded with skepticism by the astronomical community until the 1970s, when American astronomer Vera Rubin made a more convincing set of observations. By the 1970s, sensitivity and resolution of radio telescopes had improved enough to allow astronomers to detect clouds of gas at distances well beyond the visible boundary of galactic disks. Armed with this new technology, Vera Rubin set out to measure the orbital speed of gas and dust at the farthest edge of the Andromeda Galaxy. What she found was that the orbital speed did not decrease as expected. Here we see an illustration of a galaxy rotation curve, showing the orbital velocity as a function of distance from the center. The red line represents the expected values. The prediction, based on Newton's law of gravitation, is that orbital speeds will be slower the farther out you go from the center, much like the planets in the solar system. The white line represents the actual measured values. What Vera Rubin found was that the orbital speed did not decrease as you look farther and farther out, as we would expect. She concluded that there must be some unseen stuff out there that is producing a gravitational field. And to make sense of her observations, this unseen matter must be distributed in a much bigger halo around the galaxy. This is an artist's impression of a dark matter halo around a galaxy. So when we look at a galaxy, what we see is the luminous center of a much bigger structure. After Vera Rubin's result, the scientific community started to take notice. And since then, many more observations of galaxy rotation curves have reinforced the conclusion that most of the matter in a galaxy is dark matter. So dark matter provides a framework onto which ordinary matter falls to form galaxies. In other words, ordinary matter clumps into the center. Let's look at clusters again. A crucial fact about the distribution of galaxies throughout space is that it is more or less uniform. In other words, the universe is smooth on very large scales. So averaged out on very large scales, the universe is homogeneous, or it is the same at all locations. And it is isotropic, or it looks the same in all directions. So when we look at a galaxy cluster, we have a pretty good chance of getting a fair sample of everything in the universe. That is why the study of galaxy clusters is so important. So let's start with looking at the ordinary matter in galaxy clusters. Most of the ordinary matter is actually in the form of very hot gas between the galaxies. These gases are so hot that they emit X-ray radiation. Here is a picture of our now familiar cluster, Abell 1689. This was taken by the Hubble Space Telescope in the optical range. So we do not see the gas because the gas emits radiation outside of our visible range. This is an image of the same cluster, but taken by the Chandra X-ray Observatory. So here we see the hot X-ray emitting gas. Now we can merge these two images to give us a complete picture of the ordinary matter in the cluster. So this is an image of all of the ordinary matter in the cluster. The yellow is the visible light of all the stars and galaxies, while the purple is the hot intra-cluster gas. And here's a breakdown of the ordinary matter. Only about 15% of all the ordinary matter is made up of stars and galaxies. The remaining 85% is the hot intra-cluster gas. So most of the ordinary matter in a cluster of galaxies is in the form of hot gas between the galaxies. So now that we've seen the ordinary matter within a cluster, let's see how much total stuff we have. Remember, if we can measure the gravitational field of the cluster, we can then calculate its mass. So from what we've talked about so far, we've seen two methods. The first is the velocity distribution of individual galaxies around the cluster. Recall this is what Zwicky first did in 1933. And the other method is by using thermodynamics to analyze the temperature and X-ray profiles of the hot gases. The results of both methods are consistent. The amount of matter is about 5 times the amount that we can account for in ordinary matter. So here is the ordinary matter that we saw in the previous slide. And this leaves us with a big chunk of matter that we cannot see, but we know must be there because the gravitational field of the cluster tells us that it must be there. This tells us that the unseen matter, or dark matter in clusters, is about 5 times the amount of ordinary matter. So let's go back to our original question. What is the universe made of? Well, we start with the Friedmann equation, where once again rho is the energy density of everything in the universe, h squared is the expansion rate of the universe, and k is the curvature of space. Now, even if we don't know what the actual energy density is, we can define a critical density when the curvature of space, k, is equal to 0. In other words, the critical density for a flat universe. On very large cosmological scales, the universe appears to be flat, or it appears to have no curvature. Well, it turns out that ordinary matter is 5% of the critical density. So, since dark matter is 5 times the amount of ordinary matter, then dark matter is 25% of the critical density. And that leaves 70% of the critical density unaccounted for. We will get back to the 70% later, but for now let's continue with dark matter. So far we've looked at the dynamics of galactic motion to convince ourselves that dark matter exists. But we need to confirm these results using a different and completely independent approach. That approach is called gravitational lensing and is a result of Einstein's theory of general relativity. Recall that light bends as it follows the curvature of space. So here we have a galaxy. Its mass produces a curvature of space which manifests itself as a gravitational field. The light from a background quasar will bend around the galaxy such that when it reaches the observer, it will appear to come from different parts of the sky and produce multiple images of the actual quasar. This is what it appears to the observer. It appears as 2 quasars on either side of the galaxy. In this illustration, we see how 4 images of an object can be produced by gravitational lensing. And this is an actual image taken by the Hubble Space Telescope, showing the foreground galaxy in the center with 4 images of background quasars. This particular configuration is called an Einstein cross. Here is another example of gravitational lensing. The foreground galaxy and its gravitational field has created multiple images of a background quasar, and these are the imaged quasars. In this case, the gravitational field of a cluster of galaxies is producing multiple images of a distant galaxy, and these are all the images of the same galaxy. Now you might ask, how do we know that these are multiple images of the same object and not just different objects? Well, besides the fact that if you look at them very carefully, they look alike, the actual way astronomers know is by measuring the distance of the images through redshift and analyzing their light through spectral analysis. It turns out that the images are all at the same distance and have the same light spectrum. Therefore, we know that they are images of the same object. Often, instead of distinct multiple images of galaxies, what we get is a stretched image. We first look at a special case called the Einstein ring. So let's say we have a foreground galaxy with a background galaxy directly behind it. The light from the background galaxy will bend around the foreground galaxy such that when it reaches the observer, it will appear to be coming from either side of the foreground galaxy. And because of the symmetrical geometry of this case, the images will actually stretch to form a circle around the foreground galaxy. Now, these are beautiful images of actual Einstein rings. And as you can see, the image of the background galaxy has been stretched to form a circle or an arc around the foreground galaxy. These are beautiful examples of gravitational lensing by clusters of galaxies. As you can see, there are many background galaxies whose images have been stretched into arcs by the gravitational field of foreground clusters. We can see a very systematic alignment of arcs all wrapping around the foreground clusters. So these images tell us something about the gravitational field of the clusters. So what are the results of gravitational lensing? Well, through careful study of all the lensed images, astronomers and physicists can reconstruct the overall gravitational field of clusters. Once we know the gravitational field, we can then determine the amount of stuff in a cluster that is needed to produce such a gravitational field. The result is that clusters must contain much more matter than can be accounted for by the ordinary matter alone. So, how much more stuff? Well, it turns out that this unseen matter, or dark matter, must be 5 times the amount of ordinary matter. Amazingly, this is the same result that we got by the dynamical approach of galactic motion. So we must be on to something. Once we've determined the gravitational field of a cluster, we can then map out where the dark matter should be within the cluster to produce the overall gravitational field. These are images of well-known clusters with dark matter maps superimposed on the visible images. Remember, we cannot actually see the dark matter, but we can map out where it should be to produce the observed gravitational field. This image is the best evidence so far for dark matter and for the way we think it behaves. It is called the bullet cluster. Observations indicate a powerful collision between 2 clusters, and that during the collision, the dark matter separated from most of the ordinary matter, confirming how we think dark matter would behave in such a collision. Now, to better understand this image, let's take a look at the different layers one at a time. Here we see it in the optical range as seen by the Hubble Space Telescope. The 2 clusters are here and here. Now we add the X-ray image from the Chandra X-ray Observatory. Remember, most of the ordinary matter in clusters is in the form of hot gases that emit X-ray radiation. What is important to notice is that most of the hot gas, and therefore most of the ordinary matter, is between the 2 clusters and not centered on each cluster. This is because during the collision, the hot gases interacted as the 2 clusters went through each other and set up somewhat of a shock front and slowed down the gases. So now let's take a look at the dark matter. This is a map of the dark matter. Remember, The map is a reconstruction of the gravitational field based on the gravitational lensing in the background. Now, dark matter does not interact with ordinary matter, so we would expect dark matter to simply pass right through and not slow down as the hot gases did. So here again is the full image. We clearly see a separation between the dark matter in blue and most of the ordinary matter in pink. Amazingly, the gravitational field is not centered on where most of the ordinary matter is, which is the hot gas, but it is centered on the clusters where there is less ordinary matter. The separation that we see can only be explained with the presence of dark matter. This image has become the textbook image of how dark matter should behave. Our last evidence of the existence of dark matter comes from the cosmic microwave background. We will not go into great detail, but I just want to give you a basic summary of what cosmologists have learned from this. Recall, the cosmic microwave background is a snapshot of the universe when it was only 380,000 years old. It is the oldest light in the universe. It is the leftover radiation of the Big Bang, and it is spread almost exactly the same throughout the universe. This image is the map of this radiation. The cosmic microwave background allows cosmologists to probe the physical conditions of the very early universe. The first thing this shows us is that at this age, the universe was very much the same throughout. This explains why today, on very large scales, the universe looks the same in all directions. The different colors we see simply represent very small temperature and density variations, which are the seeds of galaxies and clusters we see today. Now, the density variations are on the order of 1 particle to 100,000 particles. And gravity goes to work on the slightly denser regions, gathering more and more particles, getting denser and denser, while the slightly less dense regions becomes less and less dense. In this way, structure slowly starts to form as the universe expands. Now, through the study of these temperature and density variations, scientists can determine the density of ordinary matter. And to explain this pattern of variations, there needs to be 5 times as much dark matter than ordinary matter. So once again, we must be on to something. So let's go back to our original question. What is the universe made of? We've just seen 3 independent methods, and they all came up with the same result. The study of galaxy dynamics, the motions within individual galaxies, and the motions of galaxies within clusters indicate that dark matter is 5 times the amount of ordinary matter. Gravitational lensing, or the reconstruction of the gravitational field of clusters given by the lensing of background galaxies, also indicates that dark matter is 5 times the amount of ordinary matter. And finally, we just saw that analysis of the density variation patterns in the cosmic microwave background also indicates that dark matter is 5 times the amount of ordinary matter. So at this point, we should be pretty much convinced that dark matter exists. We don't know what it is or how it behaves, but we should be convinced that it exists. So we're pretty convinced that dark matter, whatever it is 5 times the amount of ordinary matter. But how do we convince ourselves that ordinary matter is only 5% of our universe? Remember, this is our original pie chart. Well, the answer is through Big Bang nucleosynthesis. As we saw in Lecture 3, Big Bang nucleosynthesis is the theory of how and when the first atomic nuclei formed in the very early universe. Big Bang nucleosynthesis occurs around 1 minute after the Big Bang, when the universe had a temperature of about 3 billion Kelvin, or about 5 billion degrees Fahrenheit. And the ratio of subatomic particles was 1 neutron for every 7 protons. Now, based on our current laws of physics, we can make predictions about conditions in the past, then test those predictions today to see if we understand what was going on in the very first moments in the universe's history. So the prediction based on Big Bang nucleosynthesis is that 25% of all the protons and neutrons, basically all the massive particles that make up ordinary matter, should be in the form of helium. The theory also predicts trace amounts of deuterium, helium-3, and lithium. Of course, the remaining 75% would be single protons or hydrogen. Now, these curves are the predictions of the abundance of light elements based on the density of matter or on the number of protons and neutrons. So this plot assumes that the abundance of light elements changes depending on the number of protons and neutrons. In other words, for any given initial amount of ordinary matter, we make specific predictions of the abundance of light elements. So, of course, astronomers set out to make observations to test the predictions. The red circles represent the actual observations, and as you can see, the observations match the predictions. Not only do they match, but they match for one specific value of ordinary matter. And you've probably already guessed. That value is 5% of the critical mass energy density of the universe. So Big Bang nucleosynthesis fixes the number of ordinary matter particles in the universe. In other words, we actually know how much ordinary matter was produced shortly after the Big Bang. Now, since we know that the total amount of matter in the universe, ordinary matter and dark matter, is 30% of the critical density, and we've just seen that ordinary matter is only 5% of the critical density, Big Bang nucleosynthesis tells us not only that there must be dark matter, but it cannot be some form of ordinary matter that we simply haven't been able to see yet. Big Bang nucleosynthesis tells us that dark matter must be some new kind of matter. So what do we know so far? Well, so far our collection of data tells us what dark matter is not. It is not some hidden form of gas and dust because it would heat up and would be visible in X-ray. It is not any other form of ordinary matter because both Big Bang nucleosynthesis and the cosmic microwave background set tight limits on the amount of ordinary matter. And it is not in the form of machos. We haven't actually talked about these, but these are basically objects that are too dim to be seen, such as dwarf stars, neutron stars, and black holes. There's been a lot of research in this area, but there are simply not enough to account for the remaining matter. And in any case, they are ordinary matter anyways. So the data tells us what dark matter is not, but it doesn't tell us what it is. So we're pretty convinced that dark matter must be a new kind of particle, a relic or a leftover particle from the Big Bang. So what properties should this new particle have? Well, of course, it should be dark. What that means is that it does not emit, reflect, or absorb light. It also means that it does not interact with itself. Ordinary matters interact. It clumps together and forms structure. Dark matter does not. It seems to be distributed in a halo, while ordinary matter condenses in the middle. The dark matter particles just pass through each other. Dark matter should be cold. In other words, it must move slowly compared to the speed of light. The speed of a particle is an indication of its mass. For example, the neutrino is so light it travels close to the speed of light. It is therefore considered a hot particle. Now, since we know that dark matter must have a non-negligible mass, it must be cold or a slowly moving particle. In addition to being dark and cold, it must be weakly interacting. or it does not annihilate easily with its antiparticle. In the early universe, strongly interacting particles easily annihilate with their antiparticles. So if dark matter were a strongly interacting particle, there wouldn't be enough of it left over today to account for the dark matter. So the form of matter we are looking for is called cold, dark matter. And the best candidate we have so far is called the weakly interactive massive particle, better known as a WIMP. So how do we go about trying to find a WIMP? There are currently 3 methods. The first is through direct detection. These are some of the current research projects. Now, all of these experiments are conducted deep underground because the Earth acts as a shield against cosmic rays and other particles that might mimic dark matter. The other method is through indirect detection. In this case, the search focuses on detecting either gamma rays from the annihilation process using the Fermi Gamma Ray Space Telescope, or by detecting neutrinos from the decay of the annihilation process. The third method is to try to make one through particle collisions in a particle accelerator. So now if you've ever read the headline, "Physicists Find the First WIMP," you'll know what it means. Now, interestingly, dark matter scientists feel that after decades of search and with ever-improving detection devices, they should have found dark matter by now, but yet they haven't. So they are starting to wonder if new dark matter theories are needed. And so we come to dark energy. Dark energy is the most compelling mystery in physics today. Understanding dark energy will very likely revolutionize our understanding of the universe. We are pretty convinced that dark energy is out there, but we don't know what it is. What we do know is that it is what drives the accelerated expansion of the universe. We will see that it turns out to be the missing 70% of the critical density for a spatially flat universe. Now, although we don't know what it actually is, we do know some of the properties it must have. It must be smoothly distributed throughout space. In other words, it is more or less the same everywhere. And it must be persistent, or it does not change, or at least changes very slowly as the universe expands. The even distribution of dark energy means that it does not have any local gravitational effects, but rather dark energy has a global effect on the universe as a whole. Before we talk about dark energy, let's briefly review what we mean by expansion of the universe. The theoretical framework for the universe starts with Einstein's theory of general relativity. General relativity tells us that space-time is dynamical. So space has a geometry, and that geometry can change. Gravity, then, is simply a manifestation of the curvature of space. The left side of Einstein's equation tells us about the curvature of space for a given amount of matter and energy, given by the right side of the equation. Now, even before he knew that the universe was expanding, Einstein realized that his equations would support a dynamical or a contracting universe. But he firmly believed in a static universe, as did everyone else at the time. So he introduced a new term to his equation called the cosmological constant. The cosmological constant was a feature of space-time itself that would stabilize the universe. The key observation of the expansion of the universe was made by Edwin Hubble. He studied the relationship between galaxy distances and their velocities. What he observed was that the greater the distance of a galaxy, the greater its speed of recession. In other words, the universe is expanding. Now, what we mean by that is that space itself is expanding. Now, at this point, Einstein abandoned his cosmological constant and called it the greatest blunder of his career. But we will see that maybe it wasn't a blunder after all. Okay, so how does the story of dark energy begin? Well, it starts with the realization that there isn't enough matter in the universe. Now you might ask, enough matter for what? What does it mean there isn't enough matter in the universe? Well, most cosmologists believe that the actual density of the stuff in the universe should be equal to the critical density for a flat universe. They define omega as the ratio of the actual density to the critical density. And if they are the same, then omega is equal to 1. By the 1980s, theoretical cosmologists were convinced that more and more dark matter would be found such that omega is equal to 1. However, by the 1990s, it was becoming clear that there just wasn't enough dark matter out there adding up to omega is equal to 1. So something was obviously wrong. Either omega was not equal to 1, or something else must be out there. Cosmologists were getting a bit desperate. They were pretty convinced that omega should be equal to 1, but the observations were simply not supporting it. So another way to measure the stuff in the universe is to measure the rate of cosmic expansion. Since every particle of matter exerts a gravitational attractive force on every other particle, we expect the expansion rate of the universe to gradually slow down. So if we precisely measure the rate at which the universe's expansion is slowing down, that would tell us how much stuff is in the universe. Here we see two diagrams. The first is for omega is equal to 1, or the actual density of the universe is equal to the critical density. In this case, the expansion would continue to slow down to infinity. In the second case, omega is greater than 1, or the actual density is greater than the critical density, and the universe eventually stops its expansion and recollapses. So which one is it? Well, in 1997, two independent groups set out to measure the rate at which the expansion was slowing down in an effort to determine how much stuff is in the universe. The two independent and very competitive groups that set out to measure the rate of expansion were the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt. Their goal was to measure the deceleration of the universe, or the rate at which the expansion of the universe was slowing down. From that, they could then determine how much stuff was in the universe to cause the observed slowdown rate. What they found was completely unexpected. The universe is not decelerating at all, but it is accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics for this discovery. The fact that the universe is accelerating came as a great surprise. Intuitively, we would think that as the universe expands, it should be decelerating because particles are all pulling on each other. So there must be something other than particles and radiation. We need some new kind of stuff to explain the acceleration. We call this new stuff dark energy. So dark energy is what drives the accelerated expansion of the universe. Now, why were people so quick to believe such unexpected results? Besides the fact that two independent groups came up with the same conclusion, dark energy answered a lot of questions all at once and made things snap together. We will only talk about one of the questions, and that is, how much energy do we need to explain the current acceleration? Recall that 30% of the universe is made of matter, both ordinary and dark. So we are still missing 70% of the critical density for omega equal to 1. Well, it turns out that the amount of energy needed to explain the current rate of expansion is 70% of the critical density. Amazing. It completes our puzzle. So now we have a pretty complete picture of all the stuff in the universe. Now we keep referring to the critical density. Recall that the critical density is the amount of stuff we need for a geometrically flat universe. So to see if our picture is as complete as we think it is, we need to test it. In other words, is the universe on very large scales geometrically flat? We make a prediction that the spatial curvature of the universe should be zero. In other words, the universe is flat. So we need to test the prediction. These are the possible geometries of space. If omega is greater than 1, or if we have more stuff than the critical density, then the universe has a closed geometry. If omega is less than 1, or if we have less stuff than the critical density, then the universe has an open geometry. And if omega is equal to 1, or the amount of actual stuff is equal to the critical density, then the universe has a flat geometry. So how do we know which one it is? Well, the answer is in the sky. Very precise measurements of the cosmic microwave background determine the curvature by measuring the angular separation between spots on the cosmic microwave background. The critical angle they are looking for is 1 degree. If the critical angle is less than 1 degree, then we have an open geometry, and the spots appear smaller than the actual size. If the critical angle is greater than 1 degree, then we have a closed geometry, and the spots appear larger than the actual size. If the critical angle is 1 degree, then we have a flat geometry, and the spots appear the same as the actual size. What they found was that the critical angle is 1 degree, so we have a flat universe. In other words, on very large scales, we observe our universe to be geometrically flat. Okay, so the big question is, what is dark energy? Well, the answer is we don't know. So then we ask ourselves, well then, what could it be? Well, the leading candidate for dark energy is vacuum energy, or the energy of empty space itself. It is a constant energy that is not contained in any substance, but is inherent in the fabric of space and time itself. It is also known as the cosmological constant. Remember Einstein's cosmological constant? Einstein was the first to introduce the idea of a cosmological constant when he could not find a solution to his equations in which the universe was static. Recall that he, along with everyone else at the time, thought the universe was static. If there were only matter in the universe, his equations were saying that the universe must contract under gravity. So he added a term which he called the cosmological constant that allowed for a static universe. Now, after Hubble's discovery of the expanding universe, Einstein called the cosmological constant the biggest blunder of his career. But now it has resurfaced as the leading candidate for dark energy. So even when Einstein thought he was wrong, he may have been right. However, there is a huge problem with the cosmological constant. The estimate of what the vacuum energy should be is 10 to the 120 times greater than what it is observed to be. This is one of the largest unsolved problems in theoretical physics. Quintessence is another possibility for dark energy. Instead of being a constant like vacuum energy, quintessence fills the universe but slowly changes in time. There are also other off-the-wall possibilities, one of which is phantom energy. In this case, dark energy increases in time, eventually ripping the universe apart. Now, this is not one of the likely possibilities, but it is out there. So we have a good model that fits the data, but we still don't know what dark energy is. So we need more experimental data. The way we see dark energy is through its effect on the expansion and evolution history of the universe. So the experiments focus on getting better data of the cosmic microwave background, the expansion rate of the universe, the evolution of large-scale structure of the universe, and galaxy clusters. And we get this data through gravitational lensing, distant supernova research, and detailed sky surveys. These are some of the current and future experiments to get better data and better understand dark energy. Now, although we don't know what dark energy is, we can ask ourselves what role it plays in the evolution of our universe. Now, so far, it has not had much of a role. It played almost no role in the early universe when first radiation and then matter were the dominant components. And only recently, within the last 4.5 billion years, it has begun to gently accelerate cosmic expansion. Dark energy's primary influence will be on the future evolution of the universe in two distinct ways. The first is that the acceleration of the expansion shuts down any continued structure formation. So the cosmic web will no longer collapse to form larger and larger structures. Ever since the Big Bang, gravity has been bringing things together. When the expansion of the universe changes from deceleration to acceleration, structure formation stops. The second effect is that it drives an exponential expansion that doubles the separation between galaxies every 10 billion years. So the universe becomes more and more empty. Not only are things getting farther away, but the space they are in is expanding faster and faster. And in time, as the universe expands faster and faster, every galaxy passes the speed of light, at which point they cross the cosmic event horizon and they become invisible to us. Ultimately, about 100 billion years from now, the only things visible to us will be our own galaxy of stars. So as we approach the end of this course, here's an interesting question. What if Einstein is wrong? The existence of dark matter and dark energy is inferred on the basis of gravitational fields we observe in the universe. In other words, every single piece of evidence that we have that points in the direction of dark matter and dark energy comes from measuring gravitational fields. But what if our current theory of gravity, Einstein's general relativity, is wrong, or at least not completely correct? Here's a historical example of similar discovery in our own solar system. When Uranus was discovered in 1781, its orbit did not exactly follow its predicted orbit. To explain this, the French mathematician Leverrier predicted, based on Newton's law of gravitation, the existence of an unseen planet beyond Uranus whose gravitational influence would cause the orbital perturbation. And as a result, Neptune was discovered in 1846. So we conclude that application of Newton's law provided us with the correct answer, so our physics was good. Now, the orbit of Mercury also does not exactly follow its predicted orbit, based on classical mechanics. So, on the heels of his success, Leverrier proposed an unseen planet between the Sun and Mercury, which he called Vulcan. However, the planet was never found. So, in this case, the current law of gravity did not provide the correct answer. It wasn't until Einstein developed his general theory of relativity, or a new theory of gravity, that we got the answers to Mercury's orbit. So could it be that Einstein's theory of gravity will one day be replaced, possibly by a theory of quantum gravity? Well, we simply do not know yet. So what do we come away with after all of this? So far we know that the universe started to expand 13.8 billion years ago from an extremely hot and dense state, which we call the Big Bang. After an initial inflationary period, the expansion slowed down for the first 9 billion years, and since then it has been accelerating, propelled by what we call dark energy. We are pretty convinced that about 5% of all the stuff in the universe is ordinary matter, 27% dark matter, and 68% is dark energy. So we can be pretty proud of ourselves for putting together a good picture of the universe that fits all of our observed data. However, many critical questions still remain. We still do not know what dark matter and dark energy are or how they behave. Why is the observed value of the vacuum energy, our leading candidate for dark energy, so different from the predicted value? And is our current theory of gravity, general relativity, correct on cosmological scales? Or will a possible future theory of quantum gravity provide us with different answers? I would like to end this lecture series with one last story and one final question. By the end of the 19th century, physicists thought that they were almost done with the laws of physics. There were only a couple of puzzles left to figure out. The first was the calculated lifetime of an atom. Based on the theory at the time, an atom's lifetime was only a fraction of a second. Obviously, atoms live much longer than that, or we would not be here. The second was an inconsistency between the two successful laws of physics at the time, Newtonian dynamics and electromagnetism. Now, physicists were pretty convinced that once they got the answer to those two problems, they would have a complete picture of how the universe worked. The answer to those questions came in the early 20th century in the form of relativity and quantum mechanics. But instead of simply completing their pretty picture, it completely revolutionized physics and opened up a whole new world. So here we are at the beginning of the 21st century. We've put together a pretty good picture of the universe, but we still have many unanswered questions. So I leave you with one final question. Will the answers we are looking for today simply complete our pretty picture of the universe, or are we on the verge of a new and exciting revolution in physics that will completely change our understanding of the universe in which we live? This ends our 6-part lecture series on cosmology, the study of the universe. I hope you've enjoyed our cosmic journey as we explored the nature of our amazing universe. Thank you for watching, and thank you for taking this journey with me.